Assalamu alaikum to you all. According to our syllabus, the next in the sequence of lectures is supposed to be on multi-way trees. However, multi-way trees doesn't have a lab. But the next topic, which is about graphs, has a lab. In fact, the next two labs are going to be on graphs. Therefore, I decided to bring forward the topic of graphs to be done first, before later on we take on multi-way trees. So we're going to start about graphs in this lecture. We'll look at the first part of the lecture. As you know, the lecture on graphs, which is chapter 8, we have it in 2 lecture slides. So for this week, we will concentrate on this first part. After that, I will also have another recording where I will explain the implementation of graph as Java code. Okay, so the topics in this first part, first of all, a motivation. Why do we want to study about graphs? And then, what are graphs? And what are the different terminologies related to graph? Just like we did with the trees earlier. Then we look at how graphs are represented on the computer in your programs. There are a number of representations, and we will choose one of them. Then we'll look at traversals of graph. Just like with trees, we need to learn how to traverse the vertices of a graph. Finally, we take on one of the popular algorithms about graph, which is called the shortest path algorithm. So this is the target for this first part of lecture about graph. So let's start with the motivation. It says here that in spite of the flexibility of trees and its many different applications, they have a limitation. And that limitation is that they can only be used to represent hierarchical relationship where you have one element at the top called the root, and then it will have children, and then those will have children, and so on. So if your problem is of this nature, then you can apply trees. Now, a generalization of tree, which is called graph, is a data structure that will lift, if you like, this limitation. So a graph is a collection of vertices and connections between them, just like trees. However, in this case, no restriction is imposed on the number of vertices or the number of connections one vertex can have over the others. We will see what I mean when we take an example in a moment. But basically in trees, usually you will see that the connection is between parent to the children. But in the case of graph, the connection can be from any node to any other node, as we shall see shortly. Okay. And because of this, graphs can represent a large number of situations from different problem domains. Okay. Let us see some of the example applications of graphs. One example, as we shall see later in this lecture, is finding the shortest path from one city to another. So you are given a road network connecting cities, and you want to know what is the shortest path from one particular city to another. This is one problem that can be easily solved with graphs, as we shall see later. Another classical problem is called traveling salesman problem. This is finding the cheapest path that passes through all the cities, okay, that a particular salesperson must visit. To give you an example, suppose you have Almarai milk company. So the driver driving one of their trucks need to visit all the supermarkets in Jubail Industrial City, for example. The question is, what route should he follow so that he will visit each supermarket but in the shortest possible way? Okay, you can extend this problem to any situation, and it is called traveling salesman problem. So this is again another example of application of graph. Another example, maybe closer to you as students, is ordering of courses so that prerequisite courses are always taken first. So you have a degree plan where some courses must be taken before the others. They can be represented in form of graph. But the question is there an easy way to linearly arrange these courses, ensuring that no prerequisite is missed? Yani, you take all prerequisite courses before the courses that need those prerequisites. Again, this is another example we shall see, but not in this lecture, in the second part of the lecture against next week. Okay, yet another example is finding the least congested route between two phones. Okay, given the connections between switching stations for the particular telephone company. What is the least congested route to connect one particular phone to another? The last example, determining if there is a way to get from one page, let's say JUC homepage, to another page by simply following the links. Okay, so again, this is another example or another problem that can be easily solved with graphs. There are many applications of graph, and in this and the next lecture we will see example of some of these. Okay, but first of all, let's take some graph terminologies. First of all, let's define what is a graph, or define the two types of graphs, two main types of graphs. The first one is called simple graph. So a simple graph, G, which consists of two sets, V and E. Okay, it consists of an non-empty set V of vertices, so, and a possibly empty set E of edges. Each edge being a set of two vertices that particular edge is connecting. Okay, so this is what is called a graph. As you can see, it consists of two sets. Set of vertices, which is called V, and set of edges. In this particular case, the edge is considered to be a set of two vertices, the vertices that particular edge is connecting. I will emphasize the meaning of set in this context in a moment. Okay, now the number of vertices and the number of edges are normally denoted by these symbols. So this is used to represent how many vertices are in the graph, and this is used to represent the size of the edges, how many edges are in the graph. Okay, now another name for simple graph, which is even more common, is undirected graph. Okay, Okay, the difference between this and directed graph will come in a moment after we explain the other type of graph. So let's take on the other type of graph. A graph is said to be directed. Okay, directed graph. Sometimes it is simply called digraph. Okay, so again it consists of two sets, V and E, where V is the number of vertices. Notice that the number of vertices must not be empty. Okay, even though the number of edges can be empty. So consists of a non-empty set V of vertices and a set E of edges, where each edge is a pair of vertices from V. So the edge is a pair of vertices that edge is connecting. Now notice the difference. Here in undirected graphs, we call the vertices connecting, that the edge is connecting as a set. Whereas here, it's called a pair. What is the difference? Well, this is the difference. For a simple graph or undirected graph, an edge is in the form set containing Vi, Vj. Now, in this case, as you know, in set, the ordering of the elements is not important. And therefore, Vi, Vj is the same as Vj, Bi. In other words, the edge connecting the two vertices is not considered to have any particular direction. It can be from Vi to Vj, or it can be considered from Vj to Vi. Okay, that's why the graph is called undirected. The edge is not considered to have any specific direction. On the other hand, in a digraph, the edge is considered to form a pair. Now, when we say a pair, here the order is important. We must have Vi first before Vj. Okay, that is not necessarily the same as Vj, Vi. Okay, so the meaning here is that the edge has a direction, and the direction is from the first vertex here, Vi, towards Vj. When we draw such an edge in a graph, normally we put an arrow to indicate the direction. Whereas for a simple graph or undirected graph, the edges will not have any arrow. So these are the two main types of graphs, directed and undirected. Now, so even though these edges are different depending on the type of graph, here we are saying unless necessary, this distinction is going to be ignored. And we're going to write an edge between Vi to Vj simply as edge Vi, Vj, without emphasizing whether it is directed or not directed, unless if it is necessary to do so. Okay, so having taken the definition of the two main types of graphs, let us explore some examples. These are all examples of graphs. As you can see, a graph can even have just one vertex with no edge at all, as shown in A here. If you may recall, this is different from trees. When I showed a similar example or diagram when we were talking about trees, the first figure there was empty, showing that a tree can be empty. Now, in the case of a graph cannot be empty. It must have at least a vertex. Okay? So these are also graphs, although they look like a list or trees, but they are also considered to be graphs. So that's why we said at the beginning, graph is a generalization of trees. Just like tree is a generalization of linked lists and so on. Okay? So these are all considered to be graphs. Now notice, this is actually one graph. It's just that there are no edge connecting from this part to this vertex, or from this part of the graph to this vertex. So some of the vertices in a graph may have no connection at all. Okay, this is what this example is trying to point out. We shall talk more about this when we look at the different terminologies. Okay, so this is also an example of a graph. It has a special name. We will talk about it in a moment. So as you can see, figures A until D, they are all undirected graphs. The edges have no particular direction. However, graphs G and H, they are examples of digraphs or directed graphs, where each edge has a direction. So this particular edge is from this vertex to this one, and not the reverse. Whereas here, the edge is considered to be from both this to that, or from that to this. Okay, this is the difference between directed and undirected graph. I will talk about these other examples in the next slide. Okay, let's take on more terminologies about graphs. First of all, a multi-graph. A multi-graph is a graph in which two vertices can be joined by multiple edges. So this is the example we just saw in the last slide. So you can see here between this vertex and this vertex, there are 1, 2, 3 edges. So if you have this in a graph, maybe each one of them is representing some different value. Maybe this could be the distance from here to there. This could be the cost from here to here, and so on. So if you have such situation, the graph is said to be multi-graph. Now in this course, we shall not be concentrating on this type of graph. We'll be simply looking at normal undirected graph and undirected graphs. Okay, so just for your information, if you have more than one edge connecting two vertices, then the graph is said to be multi-graph. Similarly, the next definition we're going to see in the next slide is that if in addition you have an edge between a vertex to itself, then the graph is called pseudograph. Pseudograph. So here, in addition to being multi-graph, we now have an edge between a vertex to itself, like a cycle or a loop. So this type of graphs are called pseudograph. Again, we shall not be studying pseudograph in this course. Our concentration will simply be on directed and undirected graphs. Okay, so that's what the second definition here is saying. A pseudograph is a multi-graph which allows for loops to occur. That is, a vertex can be joined with itself by an edge. Okay, next we define the term path. Path, I believe we saw the same in trees, is essentially the same. A path from V1 to Vn is a sequence of edges, edge V1, V2, edge V2, V3, and so on until edge Vn minus 1, Vn. Okay, so sequence of edges between V1 to Vn. And for simplicity, it is simply denoted as V1, V2, V3, and so on until Vn, without repeating the word edge. Just list the sequence from the starting vertex until the ending vertex. This is called a path. No different from the meaning in terms of trees. Now, if in a path the starting vertex turn out to be the same as the ending vertex, and no edge is repeated in the sequence, then the path is called a circuit. Notice that here it says no edge is repeated. It didn't say no vertex is repeated, just no edge is repeated. Okay, so let's see an example in figure 1G, example of a circuit. Maybe before we go back to figure 1G, let's explain the next term as well, so that we don't go back there twice. If all vertices in a circuit are distinct, okay, so here it says no edges. Now here it is saying also if no edge is repeated. So here again it is saying in addition, if no vertices are repeated, all vertices are distinct means no vertex is repeated. Okay, then in that case the path is called a cycle. Okay, so as you can see, all cycles are circuit, but not all circuits are cycle. Okay, let's take an example and see, or let's go back to our example to see the difference. Okay, this figure G is showing us example of a circuit. Okay, take the non-dotted lines, start from anywhere. Let's say from here. So we go here, and then we go here. Okay, then we go here, and here, and here. Notice we are coming back to this vertex, so this vertex is repeated. And then we go here, and then finally we went back to our starting point. Okay, so the first condition is met, that the starting vertex is the same as the ending vertex. Okay, there is no repetition in age. This is the second condition. So we have what is called a circuit. However, there is a repetition of a vertex, and therefore this circuit is not a cycle. All right. However, here we're going to have a cycle, no repetition of vertex and no repetition of age, and the starting vertex is the same as the ending vertex. So again, let us start from here. So from here we go here, then we go here, then we go here, we go here, here, and back here. Okay, so as you can see here, there is no repetition of vertex and no repetition of age. So this is what is called a cycle. Okay, so essentially a cycle, as you can see, is basically meant to be like a cycle, no repetition of age or vertex. But if you have something like this, so there's repetition of vertex, then it is called a circuit. So a circuit, the vertices may repeat, although the edges must not repeat. Whereas in a cycle, both the vertices and the edges must not repeat. So this is what the last definition here was trying to explain. Okay. Finally, not finally, but another definition. A graph is called a weighted graph if each edge has an assigned numerical value as its weight or cost. Now, we don't have this example in that figure, we will see it later. But basically what it is saying is if each edge has an assigned numerical value as its cost or its weight, then the graph is said to be a weighted graph. Of course, we will be interested in weighted graph in this course. Okay. More definitions. A graph with n vertices is said to be complete. Remember, we had definition for complete tree and full tree. Okay, now we also have a definition for a complete graph. So a graph of n vertices is said to be complete, and it is normally denoted as Kn. If each vertex can be connected directly to any other vertex. So there is a direct connection from any vertex to every other vertex. You don't have to pass through another vertex to reach that particular vertex. Okay. There's an example of this actually in the figure. Let me show you. This graph number C is actually a complete graph. Okay, from any vertex like this one, we can reach this, and that directly. Similarly, from here, we can reach that, and that. So if you can reach a vertex directly without going through any other vertex, and that is true for all the vertices, then the graph is said to be complete. Obviously, you can see this graph is not complete. Okay, there is only a connection from this to this vertex, not to any other. Okay, so that's the meaning of a complete graph. Now there is a formula for finding the number of edges in a complete graph. A nice, interesting formula. So the number of edges, size of E, in a complete graph is defined as follows. E is a combination of the size of V, the number of vertices, and 2. Okay, as you may know from mathematics, combination of size of V and 2 is defined as V factorial divided by 2 factorial times size of V minus 2 factorial. Okay, this is the definition of combination mathematically, but actually this can be simplified because, let me try and simplify it. Okay, the top V factorial can actually be written as V times V minus 1, okay, times V minus 2 times V minus 3 and so on. Or you can just stop here, factorial, times V minus 2 factorial. Now divide it by the bottom. Okay, 2 factorial is 2 times 1 times V minus 2 factorial. You can see the reason why I stop here, because now this can cancel out this, so that we are left with V times V minus 1, okay, divided by 2 times 1. And this is what we have here. When I say V here, I mean the size of V, number of vertices in the set V, times the number of vertices in the set V minus 1 divided by 2. For example, the complete graph we saw there in the other example in the figures, okay, it has 1, 2, 3, 4, 5, and 6 edges. Can we get this from this formula, knowing that the number of vertices is 4? 1, 2, 3, 4. Well, let's try the formula. According to the formula, the number of vertices is the number of edges rather is the number of vertices, which is 4, times the number of vertices minus 1, which is 3, divided by 2. Okay, obviously 2 go into 4 2 times, and 2 times 3 is 6, as we just counted here. The number of edges is 6. 1, 2, 3, 4, 5, 6. Okay. Can we do the same? For example, if we increase one more vertex, so the number of vertices is 5. Okay. Okay, we already have 6 edges, so let's try and connect this additional vertex to all the other vertices and count the number of edges. So 7, 8, I'm sorry, this my pen is not working as I want. So we have 7, 8, 9, and 10. So in other words, if we have 5 vertices, there should be 10 edges. Can our formula give the same result? Well, let's see. It says size of V, which is this time is 5, times that minus 1, so times 4, divide by 2. Okay, as you can see, 2 goes into 4 2 times, and 5 times 2 is 10. So the formula is always correct. If you know the number of vertices in a complete graph, you can easily compute the number of edges using that formula. Okay. Okay, the next definition is about a subgraph. So a subgraph for a graph G is another graph G prime where okay, so that subgraph G prime consists of 2 sets also, V prime, E prime, but such that V prime is a subset of V and E prime is a subset of E. Okay, so this is natural definition. A subgraph simply means a part of a graph. Okay, so all the vertices in this subgraph, they are also part of the bigger graph, and all its edges are part of the bigger graph. In that case, this smaller graph is called a subgraph. Okay. Okay, another definition, 2 vertices Vi, Vj are said to be adjacent to one another if the edge V1, Vj is a valid edge. In other words, if there exists an edge connecting these 2 vertices. So 2 vertices are said to be adjacent if there is an edge connecting them. Okay, the edge connecting the 2 vertices is said to emanate, so this is another term, is said to emanate from Vi and is said to be incident to Vj. Now, this distinction is important if your graph is directed, because as we know, in directed graph, there is a difference between Vi, Vj and Vj, Vi. Okay, so for undirected graph, the edge is considered to both emanate from Vi and also from Vj because there is no arrow. Okay, it's just connecting the 2 vertices. Okay, and also is considered to be incident to both Vi and Vj. But for a directed graph, so if you have an edge Vi, Vj, so the arrow is from Vi to Vj, and therefore the edge is said to emanate from V1, and it will terminate in Vj, therefore the edge is said to be incident to Vj. Okay, we will see more example of this as we continue. All right, so that's about edges. There's another term related to vertices this time. The degree of a vertex V, degree of V, this is how it is denoted, is the number of edges incident to V. How many edges terminate at V? That will give the degree of V. So again here, there's a distinction between a normal undirected graph and a directed graph. If it is undirected, then we just use the single term degree of V. But if the graph is directed, then we have to distinguish between in degree and out degree. Okay, so in degree will be the number of edges coming to a vertex, whereas the out degree will be the number of edges going away from the current vertex to the other vertices. Okay, again, this distinction will be more clearer when we take examples. The last definition is what is called isolated vertex. If a vertex has degree 0, then the vertex is said to be isolated because there is no edge coming to it. Just to make this related terms clearer, let's go back to our example. Okay, let's start from the last example. So this vertex, as you can see, is isolated because no edge is coming to it. Its degree is 0. Okay, so it's considered to be isolated. Okay, now for undirected graph, there is no difference between emanating edge and incident edges. Okay, first of all, let's talk about adjacent vertices. Okay, so this vertex and this vertex are said to be adjacent because there is an edge connecting them. Okay, also this one, also this one, this one, and so on. So two vertices are said to be adjacent to one another if there is an edge connecting them. And then the number of edges coming to a vertex is considered to be the degree of that vertex. So here, the degree of this vertex is 5. 1, 2, 3, 4, 5. Okay, in this case, there is no difference between in degree and out degree. Okay, now let us look at a directed graph. For a directed graph, we don't just talk about degree. We talk about in degree and out degree. For example, this vertex has in degree of 2. 1, 2. How many edges are coming to that vertex? Okay, and also it has out degree of 2. How many edges are going away from this vertex? This and that. Okay, so this is the difference. If you consider here, it has 2 incident edges, so its in degree is 2, and it has 1 emanating edge. Okay, so its out degree is considered to be 1. So I hope this explains those terminologies. Okay, now the next topic we're going to consider is representation of graphs. How do you actually represent a graph in your program? There are 3 popular representation methods, and they are called adjacency list, adjacency matrix, and incidence matrix. We will explain each of them, and then I will tell you the one we're going to adopt in our lab. It's actually going to be adjacency list. So let's start with adjacency list. What does it mean? Adjacency list representation specifies all vertices adjacent to each vertex. Okay, so it's going to be representing the graph in terms of the adjacent vertices. So for each vertex, how many other vertices are adjacent to it? Now this can be represented either as a 2D array, as you can see in this example. So consider this graph, okay, consisting of vertices A, B, C, D, E, F, and G. You can represent it using adjacency list, using a 2D array, where for each edge, so the edges will form the row, if you like, the vertices will form the row, and then for each vertex in the column we list the vertices that are adjacent to it. So for example, A is adjacent to C, D, F. So we list those vertices along the row A. Similarly, vertex B is adjacent to D and E. So we list the vertices along the row for vertex B, and so on and so forth. Okay, for D, for example, you can see it's adjacent to A, F, B, E. So we list all the four of them here. G, however, is not adjacent to any vertex. So there is not going to be any entry in this row. Okay. Usually, of course, if this is an array, it means the other cells that do not have any entry, they will have zeros. Okay. Yeah. So this is basically how you can represent graph using adjacency list and using 2D array. You may also decide to represent it as shown in figure C here, using linked list. Instead of using 2D array, you can actually use a linked list of linked list to represent the graph. So here we have a node for each vertex, in the main linked list. But the linked list contain linked lists, where the linked lists here are the linked list of vertices adjacent to vertex A here, for example. Okay, similarly here, another linked list, and so on. So instead of using 2D array, we can also use linked list of linked list. Of course, there are pros and cons in the two approaches. Here, as you can see, memory is wasted for the extra cells that we don't have any vertex. Okay, but here no memory is wasted. The linked list will stop here since there are no more nodes. So you will be saving space. But what is the disadvantage? You cannot access an edge directly. For example, to know whether there is an edge DA, you have to follow through the list from vertex A. Go to A, go to B, go to C, go to D, and then go through this list and see if you can find A. If you can find A, it means there is an edge DA. So you cannot access the edges directly if you use linked list. So you are wasting time. So we are sacrificing time to get more, to economize on space. Whereas here, it is a 2D array. If you know the dimension, you can directly go to each element. So it's faster, but at the expense of wasting space. This is a typical situation in many data structures. You have to sacrifice between the two, either space or memory. We're going to see that in our own implementation. I will mention that in a moment after we look at the two other methods. We're going to try and compromise, take a middle way between these two approaches, rather than using a completely 2D array or a completely doubly linked list of linked lists. We will try and use an array of linked lists. So that will be taking advantage of both speed and space. I will explain that after we look at the other two methods, adjacency matrix and incidence matrix. Okay, so let's look at adjacency matrix representation. Here we represent the graph again as a 2D array. Simply create a 2D array of dimension size of v times size of v, and represent each element in that 2D array to be 1 if there is an edge, or 0 if there is none. So it's a 2D array of binary values, either 1 or 0. For the same graph, this is how you can represent it using adjacency matrix. So both rows and columns will have the vertices. Okay, here we have vertices A to G, so A to G here, and similarly here. So now for each element here, we indicate 0 or 1 depending on whether there is an edge. Obviously our graph is not a pseudo graph, there is no edge from a vertex to itself, so all the diagonals are going to be 0, and there is no A, B, B, C, C, D, D, and so on. So the diagonal is automatically always zeros. Okay, now for the other cells, we will put 1 if there is an edge, AC for example. Of course there is AC. Okay, but there is no AB, so AB will be 0. See, there is no edge here, there is no AB. Okay, but there is AD and AF, AD and AF. So we put 1 against those, and zeros against all others. Similarly, when you go to row B, you only put 1 1 for the edges that exist. So there is BD and BE, as you can see here, BD, BE. So this is how to represent a graph using adjacency matrix. It's simply a 2D array of size number of elements in V times the number of elements in V. Okay, a square matrix. Obviously, as you can see, there are many zeros in this array, and therefore there is a lot of wastage of space. Okay, another way is called incidence matrix. So rather than adjacency matrix, we look at the incident edges. Okay, so here it's not going to be of size V square, where V is the number of vertices. No, it's going to be of size V times E. Okay, number of vertices times the number of edges. Okay, where we put again 1 if there is an edge, EJ, incident to the vertex VI. Otherwise, we put 0. This is the example. So on the rows, we have all the vertices, and on the columns, we have all the edges, not the vertices again, the edges. So if you count here, we have 1, 2, 3, 4, 5, 6, 7, 8 edges. Put all of them here. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So for each row, for each vertex, if that edge connect to that vertex, you put 1. So obviously AC and AD will have an A, so there will be 1, and also AF, but all others will be 0. Similarly, for B, put only edges that are incident to B. Okay, edges that terminate at B. In this, that connect to B, since we are talking about undirected graph. Okay, it's actually both incident and emanating. Okay, so we have DB and EB. So both these two edges are incident to B. Therefore, you put 1 against them. Okay, and so on. So again, as you can see, there are lots of zeros. Okay, you may save a little more space if there are fewer edges in your graph. because then the 2D array will have small number of columns. So it may be a little more efficient than this one if there are fewer edges. But if there are more edges, then the number of columns here are going to be more, maybe even more than the number of vertices. So in that case, you may not be saving anything. Either way, there are many zeros being stored here. So we are allocating space for an edge that doesn't even exist. This is the problem with both of these two approaches. As I mentioned here in this note. Say note, both adjacency and incidence matrix methods, they will give you direct access to the edges. Okay, so faster access, but at the expense of space, at the expense of wasting space. Whereas adjacency list saves space at the expense of access time. So if you are asked a question to compare between these two, this is the answer. Now let's take the example showing the way we are actually going to do our representation. It says, in our implementation, we shall adopt the adjacency list method. However, we shall take the middle ground of not using completely array, so we don't use 2D array, and also not using completely linked lists, so we're not going to use linked list of linked list. Rather, we're going to use array of linked list, as you can see in this example. Okay, so for this graph, we're going to have an array, 1D array, not 2D array. But the content of that array is going to be linked list. So the linked list will contain the edges that connect to that vertex. Okay, so you can see here there's going to be an edge connecting 0 to 1. Okay, and also 0 to 2. Okay, so 0 to 1, this is the corresponding vertex. This 3 is the weight of the edge. Okay, and similarly here there is 0, 2, and the weight is 5, and so on. So this is how we're going to represent our own graph. Okay, using array of linked list. So it is taking advantage of both, because now to check if there is a vertex, or rather if there is an edge 3, 4, for example, we can come directly to this cell 3 and then search if there is a vertex 4. Okay, so the searching is much faster than if we had to start from the beginning, go until you find the 3 and then start going until you find the 4. No, because this is an array, we can come directly to 3 and then search that linked list to see if there is a vertex containing 4. Okay, so this is the representation we're going to adopt. It's adjacency list, but using array of linked lists. All right, we shall see this in more detail when we look at the implementation of graphs in the next lecture, which I will record after this. But for now, let's go to graph traversals. As in trees, traversing a graph consists of visiting each vertex one time, only one time. Okay, I want to visit each vertex, maybe to print them or to do something with them. Okay, this is called traversal. Now, however, the simple traversal algorithms that we use in trees cannot be applied directly to graphs because of two problems. We have to do some modification for us to be able to apply them to graphs. The two problems are: one, graph may include cycles. If you recall, in tree we start from the root and then we keep going. If you're doing a depth first, we keep going to the left and deep until we cannot reach any vertex anymore. Then we come back and take another track and so on. Now the problem with that is in graphs, a vertex may take you to another vertex that you have already visited before. So you may end up in an infinite loop. Okay, so that's what we are saying here, that graph may include cycles. Hence, the tree traversal algorithm will result in an infinite loop. Okay, this is one issue. Now, to prevent this particular issue, what we will have to do is we will need to keep track of the vertices that we have visited, usually using Boolean array. So when we visit a vertex, we will mark it as visited, so that even if the algorithm say we should go there again, we should say no, we have visited it before. Okay, so that will allow us to prevent going into an infinite loop. We will see this when we come to the implementation. Now, the second problem you may have comparing with trees is that in graphs, a vertex may be isolated. So if you only rely on reaching a vertex by following the edges, this particular vertex has no edge linking to it, so you will never be able to visit it. Okay, that's what we're saying here, which means some parts of the graph are left out if we follow the tree traversal algorithm directly. So again, to prevent this from happening, we will have to repeat the traversal from different starting points. In tree, we just start from the root. Okay, so here, after we start from a particular vertex, we have to check after that we reach a stopping point. Have we visited all vertices? If not, we have to start the traversal again from the next unvisited vertex. So we will be repeating the traversal until we visit all the vertices. Again, this will become clearer when we look at the algorithms. Okay, so with this modification, we can easily modify both the depth first traversal and breadth first traversal algorithms that we saw in trees. We can modify them to work with graphs as well.